we can get started. I bet all the key clicking is also probably painfully loud. What? Ah, okay. Yeah. Okay, tech news. There wasn't too much. I can go back through the emails if you guys really want to see it.
Are we recording?
Yeah, I'm recording right now. And I don't plan on doing any editing, so like I'm just gonna post it. So try not to yell anything too obscene in the video, I guess. No. Okay, what news do we got? Robot to MacGyver, simple tools by accessing objects form. What? People are doing scary stuff with robots, and it's kind of getting concerning a little bit. Thanks to new technology that enables us to create simple tools. Okay, well, we got a video here. That's always exciting.
You could say.
The broader goal of this research is to enable robots to inventively solve problems using parts available to them, and this is colloquially referred to as MacGyvering. There's also a TV show that's based off of the same term. Specifically, this work looks at enabling robots to construct tools using parts available to them when the tools that they need for a task is either inaccessible or just unavailable to the robot. The robot here creates two different tools, a squeegee and a spatula. In order to reason about which parts to use for the construction of the tool, the robot looks at the shape of all the pieces available to it, as well as how the different pieces can be attached to construct a tool. Once it has the tool, it ranks the different possible part combinations to see which one works the best, and then goes ahead and constructs that. It also tests the tool to check if it works. This research was actually inspired by this amazing story that took place on 4430, where the astronauts had to fashion a carbon dioxide filter using parts available to them because the carbon dioxide levels were building up. This was a very stressful situation for the astronauts, and it took them several days to actually come up with a viable solution to constructing carbon dioxide filter. So inspired by that scenario, we'd like robots to be able to assist humans in these situations by suggesting possible solutions, and since robots are often free of the cognitive stress that humans encounter in these situations, they can come up with interesting solutions that might work and make this very large computational space a lot more attractive. Currently, our research is able to enable robots to construct simple tools, but as we move forward, we want them to be able to construct more complicated structures, the kind that humans often build. An interesting example of this would be the Goldberg machines, which involves reasoning about different aspects like physics and chemistry. And so, as we expand this research, we want robots to be able to reason about these different aspects to construct more complicated structures.
Interesting. Oh, Georgia Tech. Okay. So that's kind of interesting.
You could say the robotics industry is becoming well armed.
Okay. God. Every time you say something, I just gotta question it. Yeah, there's a lot of robotics. People are starting to put robotics and machine learning together, and it's making very interesting projects. If you're interested about that kind of thing, there's lots of current research and tools being made available online for pretty much everything. Yeah. Was there anything else in the news you guys saw that was interesting? You can Google it. Anything? No? Okay. Huh? None in particular? Oh yeah, I guess I was supposed to, we can bring this up. So there's a, so this is like a math competition. So it's the Scudem IV 2019. It might, I don't know if, I think registration is still open. Cool. For students. Wow. Okay, that's not what I wanted. I guess this is the challenge. Local sites. I'll talk about it and then maybe people understand what they're interested in. Essentially what it is you get a problem. I think it's a set of, you get 3 different problems you can solve, and you're going to look through some research that's related to that problem. And the team will work at their institution, blah, blah, blah. And each team will prepare a 10-minute presentation. Basically, the whole point is you come up with some differential equation model for whatever the problem is. You create a presentation and try and defend why you think your model is good. So it's an interesting project. It's very math-oriented. This isn't like, okay, now write a computer simulation for it. It's more just solve the problem or create an equation you think solved the problem, and then video yourself saying why you think it's a good idea. So if you're interested in that, we could try and get something together. I didn't realize there's a $100 registration fee. Yeah. But so if we do that, we need a faculty member, probably somebody from Toledo to sponsor it, and then Toledo would pay for it, I'm sure. But yeah. It doesn't seem like it's terribly exciting, and it's not really programming. So, yeah.
How far is it from here?
It's, you video yourself wherever you are, and then you send them the video. Yeah. So, I'm gonna move on then. Figure I had to at least bring it up. Other things to bring up, hackathon is next week. We're still trying to figure out carpooling for various people. So if you're interested in going, drop a comment in the chat. There's a Kent Hackathon chat, and we'll try and figure out. I think last time what we did is everybody kind of met up here when they were ready, and then people just left when they could. It's going to be a lot of fun. This is a pic from the last one we went to. Oh, that was a good day. Yeah. There was only 5 of us. Last time when we went to the Case Hackathon, we had basically 3 tables that looked like that. And then what you can't see is the inflatable sofa that's on the side. And you can't really see the Nintendo Switches. We had Super Smash Bros. on the TV prior to that. At some point, we definitely did.
Tom, would you mind describing the inflatable couch?
It's
a rubbery, bouncy fun vibe.
Oh, okay. It's perfect for Super Smash Bros. Okay, I'll leave it at that. So yeah, drop a comment in the chat if you want to go, because we're going to try and figure out carpooling. So if you do want to drive, say something. If you don't want to drive, definitely there's plenty of people that are going that are more than willing to drive. So the whole point, you go there, you can't, is you basically are surrounded by other programmers, and you get to spend the whole weekend working on something fun that you actually care about, as opposed to just doing a coding project, which can get boring for most people. Especially because you're working alone, you get to work in a group here, which is always exciting. Okay. I think it's time to get into some high-performance computing. So the majority of these slides, I went to a conference. It was live streamed from various places. I was at the Case. They had a live stream feed there. And all the videos are available online. I'll drop the links, and I'll drop all the references for all this below. But a lot of these slides are just copy and pasted from the various speakers. They covered basically everything to get into high-performance computing. High-performance computing is, instead of using your puny little laptop or desktop, you get to go into the big remote machines like what's the specs for Stampede 2, which is one of the big. They have peak of 18 petaflops of performance. A floating point operation per second. So that's 18 times 10 to the peta, so that'd be 15
Is that above or below exa?
below exa. 18 times 10 to the 18th operations, floating point operations per second. Yeah, it's up there. Yeah, that's a lot of performance speed. They have, so then it's kind of like that's built up of a bunch of other computers. And so these are the specs for each of the individual. Of the 4,200 nodes on it, there's 68 cores on each node with 96 gigs of RAM and 16 gigs of high-speed RAM. Yeah. Yeah, maybe. Storage capacity of 31 petabytes. So here's the question, is what do we do with this? This can do a lot of things, but how do we make use of it? And so let's see, is there a marker? Yes. So here is the main thing. Oh, now I gotta move this stupid camera. See if I can move it in a way that will work. I think I yanked a cord out, but it's okay. It's this one. And I gotta figure out how to turn this one off. Do you guys remember how to turn these off? Like the individual ones? I'll turn them both off now. Oh, it's okay. Okay, so let's say we have a bunch of math to do, because that's essentially what. Okay. Turn off the system. Okay, because that's essentially what computers do, right? They do a lot of math. Okay, so we have a list of numbers. We'll just do 1, 2, 3, 5, 6, 7, but you get the point. It would keep going for a while. We could theoretically do 100. Okay, and let's say we want to do maybe a little bit more complex math. We want to do something like natural log, just so that it's a bit more complicated. You can't just immediately put it in your head. So if we're running it on your machine, it has a couple cores, but for the sake of argument, we're going to assume it has one core on the CPU. Okay, and the entire purpose of a traditional machine is to go through these one at a time and do it as fast as possible. So because it's designed to do it one at a time as fast as possible, it does it relatively quickly. So we could run through these, and it would take, I don't know, maybe a millisecond or something. But if you notice, we were able to list all these out at the beginning. This is a key point with using high-performance computing is if we can come up with all the math to do at the same time, then we can use this ridiculous amount of computing power to do it all at the same time. So while it might have taken 1 millisecond to go through this sequentially, if we had a computer with 48 cores on it, we could go through them all in 0.01 milliseconds. Something ridiculous. So that's really cool if we could do it all like this. The problem is there's a lot of things that don't work like this. So let's say we're modeling weather patterns, because that's actually, I think, one of the things that runs on Stampede too. Well, so we calculate all the pressure zones for this entire huge thing, and theoretically you can do them all at the same time, because it's, theoretically at the same time. But the problem is the next time step you do in that simulation is based on the previous one. So you have to do this balance of how much can I do all at the same time versus how much can I do, how much do I have to do one after another? And so that's really the crux of high performance computing, is trying to figure out how much of it you can do all at the same time and how much of it you will absolutely have to do one after another. So let me pull up the slides again and wait for the projector to cool down. So maybe turning them off wasn't the best idea. It's okay. Other things that are used for high performance computing, obviously artificial intelligence. And big things with that is, well, when you're training a model, you give it 1 million data points. The cool thing about machine learning is you could do all 1 million data points at the same time. And that's how you can get really big boosts out of these huge machines, is when you do that sort of thing. There's a couple other fancy techniques they can do that I think I have a slide for. So let's see if we can get this up and running. It's warming up. That's annoying. Perfect. At least I think it's still running. Yeah, it's still recording. Beautiful. Okay. High performance computing. Come on. So this next slide, it's pretty much what modern computational neuroscience is. There's 3 key parts when it loads up. Okay, we'll copy HTML. Perfect. Okay, there's 3 big parts of modern computing, really. There's simulations, which are things that I said, it's mathematical models of the world. It's the weather prediction stuff. There's the machine learning and AI, very big. You wouldn't be able to use a lot of the things you do now as easily as you do without machine learning. And obviously data analytics. If you've heard of the term big data, that's what it's referring to. And it's how do we analyze this huge amount of data that we've been collecting? Okay, so you kind of understand what's the point of high performance computing, what do we need to do, and now we have to ask how do we get there? So parallel programming, it's necessary. So this is another thing that you can kind of see is looking at how the CPUs, GPUs, and the last one's tensor processing units. So a lot of those, the big high performance computing, they have GPUs instead of CPUs. Reason being, they have a lot more cores. We're going to try and maximize this amount of stuff we can do at once. And so while a CPU does one data point times another data point, what a GPU can do, since it has a lot of cores, we can do kind of vector math all at the same time. We can do multiple pieces at the same time. And then when you get to tensor cores is where it gets crazy, where you're doing matrices of work at the same time, which is relatively new. It's in some of the RTX cards, if you've heard about those ones. They have tensor cores, which are quite exciting. The other key thing is, well, we have to store the data in our simulation when we do it. And there's a couple of different ways to do it. I'm not going to go in too much depth on them, but you can kind of just see how each one kind of structures where the cores are in relation to RAM and how they're related to each other. Shared memory, obviously, every core has access to one big piece of memory. With distributed cores, each core has its own little bit of memory. And things between them, if you look between shared memory and distributed memory, you'd be like, well, what makes you want to pick between one and the other? And with distributed memory, each one can't access each other's one. And that may be a good thing or a bad thing, depending on what you're trying to do. So if you don't want to have to deal with making sure that one core doesn't corrupt another core, because that can happen, especially because you're going to be doing so much at the same time, then sometimes it's nice to have distributed memory for certain tasks. Sometimes you need the shared memory because you're sharing a lot of memory between tasks. Or sometimes you want to go for the hybrid architecture, which is what a lot of things are doing, where you get benefits from both. Okay. Now we can get into more of the fun stuff. Can we start actually applying this? Where does it stop becoming this great selling point for businessmen, and where is it actually becoming where an engineer gets to do something fun? So we're going to start off with simple multi-threading, that idea of trying to have multiple threads, multiple things doing work at the same time. And then we'll move to GPUs, where we're trying to push the limits of what hardware can do. And so the first technology we can use is called OpenMP. It's relatively simple. Essentially, you take all these parts of code that I'm going to show you it's pretty simple to tell where you have pieces of work that can be done all at the same time. And from that, you can relatively easily add a little bit of OpenMP code. You'll see it's like a little directive, which will make sense on the next slide. But essentially, it takes certain chunks of code and just instantly makes all the threads for you and does all this work spreading for you, and then puts them back together when you need to keep going from sequential parts. Because again, not all of your code is going to be able to run parallel. Some of it has to be run sequentially. So here's how you make your code run on a supercomputer, buddies. So we have a basic for loop where they're doing some work on a whole set of values. So there's this variable x has 256 pieces of data in it. And then they're looping through each one at a time, which is what this for loop does. Looping through them one at a time and doing literally some work on them. What you do with OpenMP, you include the header file, you basically just include the libraries for it, and you add a directive, which is just this pound pragma, and then there's a couple other keywords you can add to it. But essentially, that one line of code took your code from running these one at a time to now over on the OpenMP, now runs all 256 at the same time. That's all it took. So it's getting actually pretty easy to do that. There's a lot of other directives you can use. So this one uses the parallel for directive, which takes that for loop and makes it parallel. There's a couple other ones that you can do if you really want to manipulate the threading and get it just to exactly how you want it to make the absolute most performance out of your program as possible.
I'm guessing this also sacrifices legibility.
I added one line. Actually, I honestly think it's just as legible. If anything, it just added another line that says, hey, I'm about to do a for loop. And theoretically, you know that everything in the for loop has to be done in parallel. So giving you that adds something to it. The other thing is it's a directive. So if you don't want to run it on a computer that has 256 cores, you can choose to compile it with or without these directives, without having to change anything. You just change how you compile it, which means you have one source code for high-performance computing and normal computing, which is extremely useful. As I said, there's a couple other ones if you want to break up your work in different ways, and you can Google them, and they're well documented on how to use each one and get optimum performance. Okay, so should you use this? The pros is it's really easy. It literally took one line, and I just cut the performance and theoretically and like down from 100% to like 0.5% or something ridiculous with one line of code, which is impressive. You also only have to deal with one set of source code, which is really useful if you're getting bigger and bigger and bigger and bigger programs that have bigger and bigger and bigger and bigger simulations. The last thing that's kind of a con for this is its simplicity means that you can't optimize it to the bleeding edge. And same, this also doesn't push it onto the GPU. This is still going to be run on, while Stampede has a 48-core node, we're going to be able to run this on 48 cores, so it'll cut the performance time into 1/48 because we're running it 48 times as quickly, essentially. But it's not pushing it onto a GPU, so we're not going to be able to get the benefits of that, which I'll get into in a little bit. So that's OpenMP. Do you guys have any questions on OpenMP?
It seems pretty straightforward.
Yes.
I did a little bit of Googling.
Yeah.
And it does seem like pretty simple.
Mm-hmm. If you want to just, if your code's running slow and you want to give it maybe a little bit of performance, and you know there's certain things that are relatively easy to do, it could literally take 5 minutes to implement this and cut your runtime down from 1 hour to 20 minutes. So it's definitely worth it.
And it takes 20 minutes of Googling.
Yeah, it takes 20 minutes of Googling, but you're going to save 40 minutes of runtime, so it's actually faster.
It's actually probably more like maybe 5.
Yeah.
Depending on how many things it down.
So, OpenMP, what if you have a bunch of threads like we talked about at the beginning, and you want to share memory between them, this is where things get interesting. So let's say I have process 1, but it needs some value generated by process 2. How do you send them? So theoretically, you could write up your own set of rules and make your own API wrapped around it so that you can send messages between processes. But MPI has already done that for you. And it's the industry standard. So MPI, also known as the message passing interface, essentially just passes data from one process to the other. And it's literally just, there's a send and a receive. There's a ton of other ones that get extremely complicated and in-depth. But those are the two basic ones. And essentially, each processor, in this case ranks, is what MPI's documentation uses. You send some buffer, which is your amount of data. You send the count for how many pieces of data that are in it, and the data type. And then you send where it's going, and maybe you give it a little tag. I think the tag is usually just like a comment of what this is in some sort, kind of like debugging. And then the communicator is like the general communicator that all the communication uses, essentially. So you send it, and then you receive it. And this makes sure that you don't have process 1 that tries to grab a piece of data that isn't ready. Or maybe it's grab data too late. It makes sure it's ready when you need it, how you need it. So it's not as easy as just throwing in the one line of code for OpenMP. But this isn't trying to be OpenMP. So what you do is at the very beginning you create a rank and you init the MPI. And from that, when you run the code, you specify how many ranks are going to run. So in this case, I could run it with 2. I think that's kind of the point with this one, where there's going to be a rank 0 and a rank 1. So we have our 2 processes, they're running, and what's going to happen is we set it up. We set up the communication, okay? We get what rank we are, we set it up so we're all ready. And then if we're rank 0, we're going to send a piece of data, and if we're rank 1, we're going to receive a piece of data. And that's all it does, okay? But you can imagine if you have something big, the really good use for this is, let's say we're trying to figure out the heat displacement of like a big piece of metal, okay? Theoretically, at any given time, we could calculate every little portion of this. So all 9 portions, 4, 5, 6, 7, 8, 9. We could calculate them all at the same time. But the problem is, well, heat transfers across this. So 1 is actually going to need to know a little bit of this, a little bit of 2, and a little bit of 4. And so what we do is we set up, okay, we'll just set up a buffer. We'll set up a piece of data that's meant to be passed back and forth between those different ones. And so now we get the benefits of processing, dividing our work across 9 workloads, so increasing the speed by 9, without having the downfall of waiting on other pieces of data. So that's MPI, the message passing interface. So should you use it? Well, do you need to pass data? I mean, it's kind of a basic question if you're using a message passing interface, but maybe you don't. Maybe you actually could have set up your equations better so that you don't need to use it. So pros is you're not going to have to create your own. It's already created and it's an industry standard. The problem is, again, this also doesn't help us with running it on the GPU. This is still going to be CPU bound. So that's not cool. We want to get on the CPU. You can combine the two. So you want to get you have MPI to use for your massive threading and passing data back and forth, and then you use OpenMP for those little for loops that you can run at the same time. So now you're just trying to, now you've multi-threaded your program, and now you're multi-threading your threads, which is really starting to push it. There's a bunch of source code. I have a couple links in here to various ones. A lot of them, yeah, this one has some C code that's meant to be run on Stampede or Blue Water system. Those are 2 different supercomputers. Oh, and there's some Fortran code in here if you want to get real fancy and you think you're all cool. So you can kind of look through them if you're interested and see what things you can do to start getting this crazy performance. Okay. Now it's time for the fun stuff. CPUs are boring and GPUs are king. And the reason GPUs are king, well, so we have a CPU core here. It's got really fancy control and really big cache, meant to be able to run one item after another as fast as possible. But then you look at the GPU, and instead of having, these four little ALUs, these four actually relatively complex ALUs, we have just thousands. I think right now, like an average GPU will have over 1,000 cores to be able to run this kind of math. And so doing this, you can do a lot more with it. It has a much higher throughput. The problem is, how do you actually get that throughput? Because we're used to programming on CPUs. How do we program for a GPU? So this is kind of the OpenMP had some directives. OpenACC is directives, but now we're going to throw it on the GPU. So you can use, there's two big ones that you can use. Is the parallel loop and the atomic, which are on this line. So the parallel loop essentially takes your loop and runs it in parallel. It's kind of like how we had 4 loops that we could run in parallel, but now they're going to run in parallel on the GPU. That's the big difference here. Is instead of running these on the CPU where we had 48 cores on a machine, now we're throwing it on a GPU where we got 1,000 cores. Yeah.
I can't read this code at all.
You can't read some Fortran, buddy?
I can't read this Fortran. It's that I can't tell what each of these variables are.
It's not important what the variables are.
Is the 1, NZM, for instance, just meaning that K goes from 1?
Yeah, K loops from 1 to NZM. The next, I'm assuming it loops, it starts at 1. So it's probably inclusive.
Oh, no, Fortran uses 1.
So the first loop goes from 1 to NZM, then 1 to NXPL, and then 1 to NCRMS. Okay? But here's the point, is we had 3 loops, and now we're going to do them all at the same time, all on a GPU, which is a lot of performance we can crank out really quickly. You notice there's also additional things. We have nested for loops here. So theoretically, if we were running this on a normal CPU, it would go through this loop all the time, so then it'd go to the next iteration of this loop. And so it would actually run a huge number of times. And so putting that kind of thing on a GPU is really useful. So how did it do all the nested loops? Well, we just had to throw one little extra command on it. So it took, now we're running on the GPU. Do you guys feel special? Running Fortran code on a GPU? What? Yeah, you just tell it how many loops to collapse. Other ones, so the atomic actually means that you can only, it's trying to force certain things not to hurt each other's memory. So let's say one process is adding $50 to your bank account and another process is adding $50 to your bank account. You probably don't want them to do it at the exact same time, because then they'll both add it at the same time, and this one will say, I added 50, and this one will say, I added 50. But then it'll actually say, you started with $100 and then tried to add 50 at the same time, you'll just have $150, because they won't see each other's work. And so that can be dangerous, especially if it's your bank account. But in these simulations, this could be very important. So that's another thing that is kind of built into all of these, is how do you make sure these threads are safe? And so adding things like this atomic update command in there keeps it relatively simple. So should you use OpenACC? Well, are you going to benefit from a GPU, or can you just stick to a CPU? And that's depends on the size of your problem. You really have to have a big problem to need a GPU. They say if you don't have 10,000 things to do at the same time, don't bother going on a GPU. That's how much work you should have ready, because the big problem here is you have to move from the CPU to the GPU, and that takes time. That actually takes a pretty good amount of time. So you say, oh, well, I got to add up like 500 numbers. I'm going to have to go through like 5 clock cycles on my CPU. Well, I could just do it all in 1 clock cycle on my GPU, but the problem is it's going to take so much time to move from one to the other, it was completely pointless. So you really do need a lot of work if you're going to use a GPU. But okay, so your problem is big. Apparently it must be important, so you are going to use a GPU. So what are the pros of using this? The pros are you can easily just add it right into your C++, C code, your Fortran code, and you'll get the benefits of a GPU if you are actually going to use them. And it keeps you away from having to use all the nitty-gritty details of knowing how the GPU works. So for instance, if you really wanted to get the optimum use out of your CPU, you'd be writing assembly code. And I'll show you a little bit. There is some stuff that's starting to get closer to that low-level end, but this kind of keeps it a bit high-level. Problem with that is you don't get to, optimize for your specific hardware. This is where you're really trying to get to the bleeding edge of your performance. This is when you're optimizing for the specific GPU you're going to be using, which people use because, well, they have simulations to run for a while. And getting into specific, sorry. Do we have any questions on OpenACC? A lot of this is relatively simple to get into, at least.
So I can't optimize for specific hardware. Is there much of a performance loss using C or C++ over Fortran?
Not that I know of.
Because they're both just code. It's just code that compiles down to assembly.
Yeah, it would actually probably depend on that point at how each compiler will deal with your specific problem. And so, yeah, keep going.
At which point it might just be better to consider which language would be better just for the sake of which one do you have to optimize the least.
Yeah. In the end, really, I mean, you're probably going to be writing about, a lot of it's pretty just simple math that you're really not writing any big algorithm for. It's just, here's the equations, I need to do this one, this one, this one. So, give or take, I'm sure you could look up, somebody's probably done each one and said, oh, well, Fortran's like 0.7% better, so like, that kind of thing, but, okay.
7% is actually pretty huge for
It can if you're running something that takes a week long to run. That could be, an hour. I don't know. I didn't do the math,
It
but
doesn't sound like a lot relative to a week, but an hour can save you an hour.
yeah. I mean, some of these people say they'll run simulations for like week, 2 weeks, maybe even a month on a high-performance computer. So, so now we're gonna get into how do we optimize for a specific processor. So you have a CPU, and we can write assembly code for that, so we know exactly what instructions are on that. And when you take assembly, you're going to learn about the hardware that goes into doing all of that. How does it look different on a GPU? Well, they break it down in a lot of different ways, and they have a lot of different cores. I don't particularly think that this is terribly useful. At least it's not that useful for me. What you can see is there's a bunch of single precision cores, there's double precision cores, there's some load and store units and some special function units, which I actually didn't know about. So there's some cores on there that specifically are made to do like sine and cosine and tangent. As opposed to doing the infinite series and doing the calculation every time, it just does it. What? Trig cores. Well, they do other things, but okay. So here's some CUDA code. So when you write code for CUDA, what you have essentially is what you call kernels. And those kernels are essentially kind of like a function kind of thing. And what you do with that is so this one we have a CUDA add, and that's going to be what we're going to call a kernel. And what it does is it adds the entirety of A, which is a big list of numbers, and B, which is a big list of numbers, and store it in C. This is complicated, yeah.
Why are these variable names so bad?
So first up, okay, so we int SZ, which is the size of the number of things, which I believe it's the size in bytes of, yeah. So it's the size of n, but it's how many bytes are in it. which you're going to need because in this you have to allocate memory on a CPU. We have to allocate memory on a GPU when we're doing CUDA. That's what the CUDA malloc does, is allocating data on our GPU. This is why it starts to take time when you're moving over to a GPU, because now you gotta allocate memory over there. Now we have to move the memory over there. You have to do the same for your CPU. So.
Why is a GPU a void double pointer and not a float double pointer?
A GPU, I believe, is supposed to be a reference to like the hardware.
Oh, okay.
It's
so you really can't type in hardware, otherwise it gets obnoxious.
yeah, no.
So is that the idea?
Yeah, it's a little confusing when you get real into it. Honestly, even the beginnings are a bit hard. But essentially what we've done is we've declared our stuff. Okay, let's say we've gotten it already. And what we do is you have to understand the number of cores in a block. So GPU divides all the cores up into blocks, and each of those blocks has a series of threads within it. And you have to understand how many threads are in a block, and then how many blocks are in your entire GPU. And when you do that, you can send those numbers in a specific way to figure out how to divide your work up perfectly across the GPU, which takes, obviously you can see it takes a bit of work, and we're just adding two things together. You can imagine how much more complicated this gets when you're doing a lot more work. So that's kind of a brief overview. Do you guys have any other questions about CUDA? Or getting all final stuff, specifically code?
What is the earliest GPU that actually supports CUDA?
So I think NVIDIA has been doing it for a while. How long has CUDA been supported? It was made public in 2007. That's the other thing about it, is it's so well supported. It also only runs on NVIDIA GPUs. You can't run this on a Radeon RX card or whatever the current one is. Nope.
Well, now I gotta get one.
No, you don't, because you're never going to need to do this.
Well, what if I am? If I start waiting?
You can rent Azure or whatever, Amazon's web services or whatever. I'm sure they have cloud computing that has NVIDIA GPUs. That's the other big thing. That's why NVIDIA has so much money and stuff. It's because they sell to the big people. They don't make the gamer market is relatively small in comparison to how many GPUs are bought by high performance computing.
Well, why are they called graphics processing units and most of the stuff they do is just matrix math?
Because that's what a graphic is a matrix. Got 'em. So, should you use CUDA? Do you need absolute peak performance on an absolutely monstrous problem? That's really the question to ask, because it's going to be a lot of work to get there. Pros, you get to optimize to your specific hardware. You're literally going to get the bleeding edge of performance. It's as high performance as it gets. You saw about like 18 teraflops numbers. You don't get that with using OpenACC or using any of that other stuff. You get it using CUDA, optimized for your specific hardware, and using absolutely ridiculous things to get there. They say the biggest bottleneck when they get to their level is it's an 80 gigabyte bandwidth between GPUs and memory. 80 gigabytes per second is your limiter, because that's what the slow part of this equation is, which is a ridiculous amount. Okay, this is kind of the hard part with it. Yes, it's optimized for your specific hardware, but you got to know what your hardware is to optimize for it. So okay. Through a couple different things. Okay, how do you use it? Like what I have a problem, how should I start making it run faster? And a lot of it, you kind of go through these three steps. Is there a library that already does this for me that somebody else has optimized? And a lot of times, especially if you're writing code in Python, or you're doing just basic math in matrix math in C or C++, there's just libraries that do it. So Keras, I think, does machine learning stuff. Matplotlib has stuff. What's the big matrix one for Python? There's matrix stuff that's optimized in Python that's written in C in the background. But there's libraries out there that might make you not have to worry about going into this depth.
Wait, a Python thing is written in C in the background.
That's what a lot of Python modules are written in, is C. If you want them to run fast, you write them in C, but then you want other people to use them. So you have a Python, you make a Python module around it.
So at least it's a bunch of fast pieces instead of a bunch of really slow pieces.
Yeah, that's why people use TensorFlow. It's because it's fast, but then it's also easy at the same time. You don't get the optimization that you get out of these different technologies. But if you're running small problems and you're running it on your laptop, do you really care? Like cooking versus going out to eat. A little bit. Because if you go out to eat, you're going to get something nice for sure, but it won't be exactly to your taste and be optimized for performance. Whereas if you go home, you can optimize your Korean beef and rice noodles. That's my go-to. And you can optimize that with the exact spice profile I want, So yeah, that's a pretty good analogy. Yeah. It is a pretty tasty GPU. Okay. So you can add libraries. That's the easiest. What's next? You can add the directives. Those were pretty easy. If you think you can get the benefits of GPU, go for OpenACC. Likely, if you don't have a really huge problem, OpenMP is going to be enough for you. If those aren't enough, I'd start questioning whether your algorithm's written properly. Maybe you can start trying to use less I/O, because those are always slow, as I said before. What up?
You could try using one of these for Olga.
Potentially, yeah. In the background, if you want to write a Python module, you can make a module that uses OpenMP and that kind of stuff, and then write the Python module around it. So, the last thing, if you really think that your algorithm is special and you want hardware acceleration to the bleeding edge on a GPU, you can start going hard on CUDA and OpenCL. But it's going to be a challenge.
Why are all these things called open?
Because they're open.
Open source?
A bit, yeah. They're also open standards. So
What is that?
I don't know. I just made it up. Here's a link. Links. I'll link this whole presentation in the Discord. This is the video series that essentially is the entire conference. If you want to listen to each one of those topics in detail, there's a video that's probably about an hour and a half long that I've listened to on each one of those individually. I covered them in 10 minutes, but if you want to go in depth, go right ahead. And there's slides. The slides and hand-on exercises. Literally, I copy and pasted a lot of the hands-on exercises and slides, and these are what these are. So if you want to go more in depth, if you thought one was interesting, particularly I think OpenMP is interesting. It's also really easy. So, yeah. Any last questions, comments, or concerns? You're gonna start using OpenMP, and you're gonna use OpenACC in your next coding project, John? Perfect. Yeah, that's when it gets fun. Okay, so the last thing before we're going to close up, I want to bring up again, is the Kent Hackathon is going to be, let's see here, today is 17th. It's going to be on the 27th. Okay. So, no, they don't get to know my location. We're going to try and get a bunch of us there. If you've never been to a hackathon, it's going to be a ton of fun. I've probably yelled at everybody to go to a hackathon at some point already.
Yes.
You get to listen to it again. Okay. So hackathons, it's probably the greatest thing you're going to get to do while you're in college, because especially if you like programming or you like computers in general. It's all the nerds gather in one location for free food, free caffeine, and free housing. A lot of free caffeine and some free swag. Got to rep the swag right now, actually. And you get to work on whatever project you want. And at the end, people come together and there's judging for who has the best project, who has the coolest idea. Usually there's pretty cool prizes given out at the end. And even if you don't make anything, The whole thing's free, so it doesn't matter. So it's a ton of fun. Highly recommend you come. We're going to try and make sure that we get some carpooling set up. So if you want, you can join the Discord. I don't know if you're already in it. You should join the Discord. Nice. Yeah, boy. Nice. Oh. Yeah, boy. You came to a meeting. Already a member. I think I made everybody an ACM member if you came to a meeting. I think. Yeet. Okay. That's all I had. Yeah. Do you like that Fortran, buddy? Fortran. Yeah. Anything else? No. Who's going to the hackathon is the real question. Do you have any ideas? You gotta come to the hackathon. We've had people write their first lines of code at hackathons.
We need an answer.
What?
What do you need to know?
If you want a ride, the sooner the better. You can sign up and there's nothing, like you can register and if you don't go, it's not a problem. I think you need to register by next Friday before the event. I'd register as soon as possible and then if you don't go, you don't go. What's up?
SQL, but it compiles.
Why? So,
It's faster and it breaks less.
yeah. If you want to ride, sooner the better. I think you need to do it hopefully by the end of this week. And even if you go, you don't have to make a project. You could just work on homework and play video games with all of us and get a lot of free caffeine.
And it's free.
It's free. Yeah. No. We've had a lot of people do a lot of different things. Ben, did you even write any code at the last hackathon?
Nah, fam.
That's what I'm talking about.
I won an Apple TV at the last one I was at, so.
Oh, did you actually go for the Apple TV?
Yeah, the Apple TV.
I went
And
with-
it's freaking awesome.
Really?
Yeah.
I don't know. These headphones. The headphones are nice. We won when we went to the Highland Hackathon. We got first place, owning it up. And you get some pretty nice prizes if you win. And you just make whatever you guys want. So if you have some random project that only you care about, cool. You get a weekend to work on it with a bunch of other programmers that are all willing to help.
We decided they didn't have any prizes up there yet, did they?
No, they don't have any listed yet, which annoys me.
Is there a link to go back to last year's? Like,
No, because they just redo the site. Oh, do they have a map up? Nice. The location for this one's pretty nice. I thought that.
I like
They have like, so it's in there's like 2 floors, so it's like a 10-story library. And they give us 2 of them. And it's like a really nice open area, but then there's also some cubicles in it, and some of them have TVs and stuff, so we hook up the Nintendo Switches to those, play some Smash. And then I'll be bringing the inflatable couch. Always fun. Got cup holders, man. It's got cup holders. No, yeah. It's a ton of fun. That's it.